Silence. Order. I have returned to the demo scene. To all those people who were so mean, I will destroy everything they got. Make me your leader, vote for evil bot.
Good morning. Well, I hope you had a better night than I. We lost 1 hour, etc., etc. So, I am Julien Gerto. In the demo scene, you might know me under the name Zavie of the group Control Test. This is my very good friend Laurent, LLB, also of the group Control Test. And today we are doing the exact same talk as last year because this was posted on YouTube and we had only one comment and the guy said, "This is crap." And I was like, okay, we're going to try to do it better. So the topic today is post-processing. So imagine for a moment you want to render an image. With your computer, you create an image, you render that to your screen. If you don't do any kind of processing at all, like if you directly render your image to the screen, the chances are it's going to look like an image that you created with the computer that you sent to the screen. And you might spend a lot of time, putting some crazy shader to it, and yet it's still going to have that CG look. It might look realistic and whatsoever, but for example, it's not going to look like, I don't have the focus now. Go back, thank you. It's not going to look like, for example, it's out of a camera like this one. Question is, why is that? So if you're doing some rendering, chances are you're using the pinhole camera model, which arguably is one of the simplest possible camera ever. This over here is no pinhole camera. This is standing on top of 200 years, or between 100 and 200 years of development, of improvement, trying to get really the best image possible. It's really not something simple as the pinhole camera. Really, it's quite the opposite of it. Like, this is really some complex thing. So you have your image and you want it to look like it's out of a camera like that. How do you do that? One thing you could do is, well, you change your camera model. You had one model that is not what you want. Well, you can switch to a model like this one, assuming you have a model of a camera like that. And even if you do, it might not be very simple to do. It might be quite a lot of work, and it might not even fit your pipeline because if you're doing some rasterization, like, it's not something trivial to do. Another thing you could do is, well, you render your image as usual with the pinhole camera model or whatever model you're using, and then you apply a series of transformation to that image, a series of modification, like filtering and thing, to try to give it a similar taste, a similar look to an image that came out of the camera you're targeting. So this would be the kind of post-processing we're going to talk about today. Before we start doing that, there are a couple of prerequisites, like some conditions you have to meet. In my opinion, there would be 3 of them. So you need a pipeline that is gamma correct. You need to have enough precision in your color buffer. And you sort of need a high dynamic range. What I mean by that is, in my opinion, it's not strictly necessary. Like, you can do some things without high dynamic range. So in 2003, we had like Tron 2.0 that was using a trick based on the alpha buffer to tell which part were like glowing in the game. So there is no high dynamic range at all, and yet you have a good effect. Much more recent game, Deus Ex Human Revolution, also uses a similar trick and uses low dynamic range, even though it's quite recent. Complete coincidence, 2011, we released a 64K intro, Felix Workshop, which uses exactly the same trick, LDR plus an alpha buffer to say, hey, this part is bright. So not strictly necessary. There are some things you can't do without it, but if you don't need them, you can still make your way. One thing you can't do without, though, in my opinion, is gamma correctness. Like you need a pipeline that is gamma correct. So the irony is on a talk about post-processing, this might be the most important point of it. So quick question over there. So in this room, could you please raise your hand if you don't really understand what I mean by having a gamma correct pipeline? Who doesn't really see what that would mean? Okay, so about half the room. So I assume that the other half knows exactly what we're talking about. So I invite you guys to talk with each other before the end of the party. Like if you have code that is doing some gamma correctness, please show to the people who are not quite comfortable with that. So what do we mean with gamma correctness? If you're going to display two colors on a screen, like you display one color and another color, and one has half the value of the other color, you might expect it to be half as bright as the other color. And if you do, you would be wrong. And the question is, why is that? Before we had those fancy flat screen LCD or whatnot, we had those huge, bulky CRT displays. CRT meaning cathode ray. So those had like a Canon beam, an electron beam, and you would, if you wanted to increase the brightness, you would increase the voltage, and that would increase the flux of electrons sent to the screen, and that would increase the display. The problem is, as Wikipedia puts it, the cathode has a strong triode effect, which means that when you increase the voltage, you don't increase linearly the intensity of the current, and as a result, you don't increase linearly the brightness. So you put twice as much value to it, twice as much tension, and you don't get twice as much brightness. So that would be why. When you read articles about gamma correctness on the internet, you have examples like about what you should do and what happens if you don't. And more often than not, I found those articles they don't have like very good illustration. You have, for example, an article about a game, and they're like, yeah, we did this super effect, and by the way, we have like the gamma correction step. And they show you the screenshot of the game without gamma correction and the screenshot of the game with gamma correction, and they're like, yeah, look at how the gamma correct one looks so much better than the other one. And often I have a problem with that in the sense that, well, it's a game, it has limitations in the rendering, so there are a couple of things that look not quite right, but you never really know when you see the two screenshots, one next to another, even though there is one that says this one is the correct one, you see, yeah, I still see some issues with the color and stuff, and you don't know if that's because of the technique, it's because of the implementation, or if it's because the artist was not so good at lighting, I don't know. So I tried to put together some very simple examples showing the difference between gamma correct and not gamma correct to try to get an intuition of like the effect it has. So here is some ray traced image. It uses exactly the same code on left and right, just one of them is gamma correct, the other one is not. So quick question in the room, who thinks the left one is the correct one? Okay, who thinks, okay, the majority of the room, who thinks the right one is the correct one? Okay, still some people. And who has no idea, like, well, whatever. Okay. So I would like you to pay attention to a couple of details. So one thing to look at is like how this area looks compared to this one. Like see here we have a gradient, here we have like much less of gradient, it looks much more constant. And here we have like a very strong switch from light to dark, and here we have like, it's much more blurry. So for reference, here is a photo, and see how the bright part looks like pretty much the same intensity all over, like all on the lit side, it's pretty much the same intensity, and look how very quickly it goes from light to shadow, like pretty much goes from white to black. So if we go back to the previous shot, like the left one would be the correct one. Another example that hopefully is maybe easier to see would be this one. So same deal, we have an image that was ray traced, same code, but one of them is gamma correct, the other one is not. So here is a hint, like I would like you guys to see this part and this part, and this one and this one. So, well, we might have problems with the projector that is not 100% awesome in colors, but still, I hope you get the idea. So, either I kept like the previous slide on the left, it's the right one, it's the correct one, and on the right, it's the wrong one, or I was like, hey, I'm going to be so smart and reverse them. So, who thinks the left one is still the correct one? Okay, who thinks, no, this time it's the right one that is correct? Okay, that makes me a little bit sad because it's still the left one that is correct. We might have a problem though with the projector because we have like the top that is blown up. So I invite you to try this at home, but the idea is like, yeah, here we have like a very white area that is not supposed to look like that, so that might have to do with the display. But the idea is, like, when you see here, like, you have a light here, a light there, and here you have like something that looks like it's more than A plus B, you know? Like here you have this light, and if you add them, you shouldn't have this much light over here, and you shouldn't have a gap like that. Like it looks, you go from gray to black to very bright again. So I'm sorry it doesn't look very obvious on the screen. Maybe like here it looks a little bit better. But I invite you to look at that on your screen at home. So yeah. So we have issues with the lighting due to gamma. Like stuff don't look quite right. We have, to put it simply, 1 plus 1 is not equal to 2 anymore when we don't have gamma correctness. You might think, okay, but that's just lighting. I'm just going to blow up the lights and I'm going to put more lights to it and that will be fine, right? The problem is that's not going to work either. The gamma is also going to affect really colors. Like you put one color, you mean to put a color and you get something else. You mean to put some yellow and you get some orange. So here are a couple of gradients from values. So we have 3 examples of them. And on the left, we have the gamma correct one. On the right, we have the not gamma correct one. So like if you put the value right like that on the screen, you get the right version. And if you correct it, you will get the left version. So you can see that they are not the same, even though like the bottom and the top one, so except for the middle one, like here you have like the very same red, and on top you have the very same blue, and in the middle you have a different color. So what I would like you to pay attention to is this part, and see how in the left we have changed the intensity of the color, how in the middle we have changed the saturation of the color, and in the right we have changed the hue, what we usually call color. On one side we have like something that you could call yellow, and on the right it's orange. It's not even the same color anymore. So we do have to pay attention to gamma, unfortunately. Like, you can't just ignore it. The question would be like, why are we in such a situation? So I said earlier that the CRT display had this function, and the thing is, the industry grew up, and this effect, like basically since our display had this gamma issue, the industry started to assume that this was the behavior of the displays, and everyone started like relying on it. Your camera is going to rely on the fact that when you display it, there is this gamma. And we switched to flat screen, to LCD, to OLED, etc., that don't have this issue anymore. But since the whole industry is already doing that, well, they implemented that this way too. So your LCD screen is like mimicking the gamma response of a CRT. And you would say, okay, but why didn't we fix that? You know, why didn't we change it and at some point say, okay, like it's over, we are going to fix this thing? The fact is that your eye doesn't have a linear response either. To take an example, you are much better at discriminating some very dark shades of gray than you are at telling apart some very bright shades of white. So the precision of your vision depends on the light intensity. And if you're going to have this kind of response of the human eye, and you have a limited precision of your display, you might as well spend that precision on the parts your eye is very good at. Like, there is no point losing that precision on parts your eye can't tell the colors apart anyway. And it just so happens that the gamma response of a display is a fairly good match to the response of the human eye. It's complete coincidence. Like, one of them has to do with the behavior of the cathode ray tube, and the other one has to do with biology and how we evolved as a species. But they match pretty well. So what could be seen as a problem turned out to be a pretty like some feature, some characteristic you might wish for. But the problem is we still have those color issues. So as programmers, as artists, as people working on a rendering pipeline, it's our job to take this into account. So the solution to that is, you want, if you're doing some rendering, you want to compute everything in linear space, because otherwise, like, your physics are wrong. So you want to compute everything in linear space, but you know that when you send the stuff to the screen, it's going to apply a gamma function. So what you do is you apply inverse gamma function, and the two are going to cancel out. So you create your image in linear space, you modify it with inverse gamma function, you send it to the screen, which is going to apply a gamma function, cancels out, you have the image you want on the screen. I'm going to stop there because this shouldn't be unfortunately the topic of this talk. So for the implementation details, like all the impacts this has on your pipeline, I redirect you to the great article by people like John Abel and people who talk at GDC, etc., etc. Now, post-processing. So I'm going to talk about just one effect, so we have some time to see it a little bit in detail. So I chose motion blur. It has like a couple of the features that you might need to when you're doing a post-processing effect. It needs it's doing multiple taps. It's doing multiple render targets. So I thought it would be a good example. So motion blur is when you have a camera, you take a picture. It's a real camera, like it's not an imaginary camera. You do have a thing called the shutter that is usually closed, and when you take a picture, the shutter opens, the light gets in, the shutter closes again. And this doesn't happen in 0 time. Like it's not we take a picture at t, it's a picture between t and t plus dt. So the shutter opens, light gets in, shutter closes. And if anything has changed in between, this is going to result in blur in your image. So in some cases, you could see that as a limitations because it's very difficult to get something still, but you might see that as like something you want because it has artistic value, because it conveys a sense of motion, and that's something that you want. So to implement that, we're going to make a couple of assumptions. So the motion blur I'm talking about here with post-processing is a velocity map-based motion blur. So one assumption is that we are going to say, okay, when we take our picture, the motion blur is linear, like everything is moving everything is moving along straight lines. So this is a reasonable assumption if the duration of your frame is small enough. Like if your dt is small enough, everything is moving along a linear path. Obviously, if you have stuff that move faster, I guess if you have things moving faster than your sampling rate, you're going to have issues. So if you have things making circular motion and your dt is big enough, you're going to have a motion blur that is not correct with regard to what you're doing. So you would have to be careful about that. A bigger assumption is we're going to ignore occlusion. And what I mean by that is, for example, if you have a white ball and a red ball, and the red ball is passing behind the white ball, in a real life motion blur, this is, even though the red ball is behind the white one, if it moves during the picture, you're going to see that like it's going to affect the final image. But the one we're going to talk about, the effect we're going to talk about consists in rendering the image, evaluating the speed of the objects, and blurring in the direction of the speed. And that means that when we take our picture, the red ball is not visible, so it's not visible in the final motion blurred image. Shouldn't be too much of a problem, but you have to, just like the previous assumption, you have to know what the limitations of the technique are. Another assumption, and that one is a really big one, that's the biggest of the three, and that's the biggest limitation of the technique. So again, the idea is, I take a picture, I render a picture, I'm going to evaluate how fast stuff is moving on screen, and I'm going to blur them. So if I have like a ball moving on the screen like earlier, I'm going to blur it along the path it's following. So ideally, I would, in a fragment shader, I would like to say, hey, this part is moving fast, so I'm going to make it bleed over there on the neighbor. But the way GPUs are made makes this very difficult. When you're doing a fragment shader, the only place you can write at is where your fragment shader is. You can't write on your neighbor. You can only write at the pixel you're dealing with. So one way to work around this problem is to say, okay, I'm going to I want to scatter, but I'm going to do the opposite and gather. So when I'm rendering my pixel, I'm like, okay, I'm going to look at my neighbor. How fast this neighbor is moving? Oh, it's moving fast. So I'm going to consider it's bleeding on top of I. The problem is, this is not correct. So if everything is moving more or less at the same speed, this is going to work because the two are going to be equivalent. But if you have like a noticeable difference of speed between objects, you're going to have artifacts. So again, limitation of the technique. Your millage may vary, so it depends on your use case. But this is the one thing to be careful about. So how do we proceed? First, we are going to need some frame buffer. So here I'm going to use some OpenGL and some GLSL, and actually I'm going to use old OpenGL style, like OpenGL 2.0, and now we are OpenGL 4.5, I think. I'm just using that because it's like easy to use as an example, but this should translate well to a newer version of OpenGL, to DirectX or whatsoever. Like, the hardware behind is the same, so the idea is the same. So instead of rendering stuff directly to the screen, we're going to render them to something called a frame buffer, which is like a data object in the GPU that you can basically see as a texture, and then we're going to display it on the screen. So we need to create that frame buffer. So for that, we're going to create an ID for it. So we tell OpenGL, okay, I want to create a frame buffer. So give me one. Then we're going to bind that object to tell OpenGL, yeah, we're going to do whatever modifications we are doing are concerning that frame buffer. And that's how we're going to set it up, and that's also how we are going to use it later on when we do the rendering. We might have several frame buffer, and every time we want to use one, we say, hey, I'm going to use this one. But anyway, so we're setting this up. So the idea is we're going to have a couple of textures that we want to attach to it. So for example, if we're doing the rendering, we might want to say, okay, we want the color buffer. In our case, motion blur, we want a velocity map. So another texture where we put the speed of the object. If you're doing some other kind of post-processing effects, you might want the depth buffer or something else, or you might want plenty of textures. For example, the deferred shading technique is very popular, and they're talking about the geometry buffer, and they say in our G buffer we have this, 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 and this. So it's all textures attached to a same frame buffer object. So here is an array of those buffers that we want to put together. And for each texture, we're going to add them to the buffer. So for each one, we're going to create an attachment, and we're going to add it to the buffer. There is a simplification over here, because otherwise it wouldn't fit in the slide. So be careful about that. The idea is, here those are color attachments, so a color buffer. But if it's a depth buffer or a stencil buffer, you will have to deal with it differently. So that's why you have this number of buffer, which is different from the number of textures. So just one thing to be careful about. But anyway, so we add those to our list of buffer with the attachment, and then we make a call that basically says, hey, the frame buffer I'm going to attach this texture to it. And when we're going to use that frame buffer, it's also going to write to that texture. And when we're done with that, we say, okay, whenever we use that frame buffer, we're going to write in all those buffers, like the array I've created. Because you have maybe one frame buffer that uses one texture, another one that uses 3 of them. So this one call tells, yeah, this is what we're going to, how many render targets we're going to use. So once we have that, we can render stuff to our frame buffer, and we're happy. Now, if you have your rendering, typical vertex buffer would be, hey, like compute the position of the vertices. So here would be the general case where you might even have some vertex shading. I don't know, like if you have skinning or something like that. So a function that gives you position of the vertex. To modify it to take into account the interesting switching line. I hope it fits on the screen. Yes. So we're going to change that to put our motion blur information. So we're going to do exactly the same thing as earlier. Like, sorry about that. So yeah, we have like a GL projection model view matrix, which is a multiplication of all 3 matrices. So we split that. We have the projection matrix and model view matrix. The result is the same. It's just for comparison. We're going to send as a uniform the transformation that was done before. Like say, if you want your motion blur to be on 16 millisecond delay, like if you're at 60 FPS, between 2 frames you have 16 milliseconds. So you want to send the position of your object 16 milliseconds before, on top of the current one. And we compute the corresponding position. So we have the current one with the model view matrix as usual, and we have the old one, the one that was 16 milliseconds before, with the old transform that we sent as a uniform. And now we have those 2 variables, and we're going to send them to the fragment shader stage, and we're going to use them to compute the speed. So I'm making some simplifications over here. Because, like for example, you have the DT over there that I use, but I've never declared. So here that depends on how you implement that. In our engine, we consider DT to be fixed. It's 16 milliseconds, no question asked. If you have a variable frame rate, then you want to send that DT the information, and you want to use it in your computations. But anyway, moving on. Fragment shader, typical stuff. So we have a function getColor, and we display that on screen, and that's it. Now we're going to say, okay, for our motion blur, we're not only going to write our color buffer, but also our velocity map. So we are going to write in the other render target the speed of the objects. For that speed, we're going to get the 2 variables that we computed in the vertex shader. They're going to be interpolated, and they give us the position of our fragment currently and 60 milliseconds ago, or whatever your dt is. And then we have our function that is going to say, so if there are physicists among you, you're going to say, hey, like a position minus a position is not a speed, it's a distance. But here I'm neglecting I'm considering dt to be constant. Again, if you have a variable dt, you want to pass it and modify it accordingly. So we have our speed. Oh wait, I'm not 100% sure it's a division. So don't trust me on this one, and please check on the internet that it's a division and not a multiplication. So yeah, we're in a homogeneous coordinates, so we have to take a w into account. So yeah, just the division, I'm not 100% sure right now. We're in the morning of the third day of revision, so don't trust me on this one. Anyway, so we have that speed. If we do things correctly, it's going to be between 0 and 1. Well, between -1 and 1, you might want to clump it. And since we're going to display it as a color, we want to rescale it between 0 and 1. So typical multiplied by 0.5 plus 0.5. So we have our speed in our color buffer. Problem at this stage, we're going to already have a bug, which is if you have a limited precision in your color buffer, for example, if it's 8 bits, so we have like 256 different values that are possible. When your speed is very, very small, like 1 out of 255, it's just 0 or 1, like this kind of length, we're going to lose a lot of precision in the direction. For example, if it's like just 1 at 30° northeast, well, the only value you have for x is 0 or 1. The only value you have for y is 0 or 1. So you have the choice between 0, 45, and 90 degrees. So at very low speeds, if we do that, we're going to have some jittering when things are moving very slow, because we're going to switch very fast between 0 and 90 degrees. So to deal with that, we have to change this line a little bit to add some precision. So there are various ways to do that. The way I use is I'm going to store separately the direction of the speed and the amount of speed, so to speak. So compute the norm of the speed, and then in our vector on one side we put the normalized speed, and on the other side we put the amount of speed. Something else you could do is use a power function. Like if you do power 0.5, you're going to move values toward 1 instead of 0. So you have like your lower speed are going to have bigger values, and you will have more precision. You might want to ask, what is the 0.0001 out of nowhere? This is for when your speed is 0. You don't want a division by 0. So if you put that, when your speed is 0, you have 0 divided by something that's still 0, but you don't have an exception. And you don't have a none in your pipeline, and you don't have like dark values that are going to bleed all over the place with typical bugs. So that's it for the fragment shader. We now have one frame buffer that contains the color as usual. We have one render target, and another render target that contains a color that represents the speed. So we can move on to the post-processing. So the vertex shader of a post-processing is really simple. You send a quad, you just want to send the texture coordinates to your fragment shader, and that's it. Actually, this is even more complicated than it needs to be. Because if you're using like an orthogonal projection, you don't even need to multiply by a projection matrix. You could just use GL vertex if it has the right coordinate system. You don't even need to multiply it. So it's really like the simplest thing ever. And you don't need to change that for motion blur. It's going to stay the same. Now, fragment shader, if you have a typical post-processing that does nothing, takes an image, display it on screen, what happens is we get our color buffer, we fetch it at the correct coordinate, and that's the color we're going to display. End of story. If we want to use motion blur, so what we're going to do is, first, we start with a 0 color, like we have nothing, it's black, and we're going to display the final color like as usual. But we're going to use the velocity maps that we created to fetch a couple of samples, like a couple of taps, from the color buffer. So instead of taking just one, we're going to take a few samples along the motion path, and we're going to add them together and do an average. So for that, we need our velocity map. We're going to fetch the speed information from that velocity map. So it's not the speed yet, because remember, we did some little bit of trickery to save it. So we can do the opposite transformation, so we get our speed, so we put back the 0. Oh, there is one missing 0. Anyway, so we put back our thing, we put it back between -1 and 1, and we have our speed. And then here is our for loop, where we compute the offset, so how far we go, and each time we add it to the current color, and we have our n samples, or whatever. In this case, the number of samples is fixed. It's n, so you say, okay, I can afford 8 taps, or 16 taps, or 20 taps, whatever. Another way of doing that would be, so the thing is, if you have a small speed, we're going to do many taps at the same place, and if you have a big speed, we're going to do the same amount of taps, but with quite a gap between them. So another approach could be, we do our taps at a fixed distance, and when we reach the end of a motion vector, we just stop. So instead of doing for, well, we still would have for I from 0 to n, but the offset would be from constant increments, and when we reach the speed, we just break out of the loop. That's another way to do it. So here is an example. So we have the usual rendering on top, and at the bottom, we render the velocity map, and the result we would have out of it would be a picture like that. So I can probably show you a live demo of it. I think we have it running somewhere. Alors attends. Okay, moving on. So here is our demo. Oh, the colors make me a little bit sad on this projector, but anyway, that's not what we're looking at. So here we have some motion blur, as you can see. For example, you see over here, we see the lines going in the direction we're going at. But if we deactivate the motion blur, so if you give me just a second to modify it, and yes, so here is without the motion blur. And here is with the motion blur. And if I remember what our key bindings are, I can even show you the, oh, that's not what I wanted to do. I'm trying to remember what our bindings are. Mince, comment on affiche les textures? Oh, okay. Okay. Yes, so here is our velocity map. So if we have things moving, you can see how the color indicates the speed of whatever is on screen. Anyway. So moving on, especially since I'm going pretty slow, so I wasted some time. Yes. No? Come on. Okay, I'm going to be able to change the slide, you'll see. Yes, I have power over PowerPoint. So the demo I just showed you is G level 1 that we released 2 years ago at Tokyo Demo Fest, so in 2014. And so here is a frame. This is the frame that we get out of the rendering, like with no modification whatsoever. This is how it looks like without any post-processing at all. After post-processing, this is how it looks like. So I'm going to show you very quickly how we achieve that, like the different effects and how they affect the image. So bear with me, I will try to do that. So, and up. So I'm going to remove this guy over here, and meanwhile, I'm going to open the editor so I can make some live modifications and show to you how this is working. Oh. Okay, this is slower than I would hope, but I'm sorry about that. Up. Okay, I'm going to move it a little bit faster. Oh. Merci. Tu peux cliquer dessus, s'il te plaît? Ah, I missed it. I didn't have focus. So let's go back to this scene, for example, which is more or less the one I have on the slide. Nope. Go back. Come on. Okay, so this is more or less the frame I had. Okay, I completely ruined the text in my editor. You don't want to see that. So let's go back to the first step. What happens when we have the thing out? So yes, this is what happens when we render the frame, plus a little bit of this that I'm also going to remove. Because those lens dirts, so to speak, are not done in post-processing. They're done directly in the during the rendering, like they're displayed on top of the scene. So if I remove them, yeah. So this is how it looks without those. So before the post-processing, we add them, and it looks like that. And then we proceed to doing some processing to the scene. So we have this image. That is the color buffer. We have this, which is our velocity map. We have this guy, which is the depth of our scene. And we have this guy that is the glow. So we took the image and we took the image and we took the light information and we made it like we blurred it to get where the light is. We have this guy, which is another kind of glow. It's a light streak, so it's an implementation of Masaki Kawase's paper. It's something like from 2004, I think. So if you look up on the internet for Kawase and you see his paper, that allows you to do like very strong light streaks. That's very cool. That's very fast. That would be the vertical version, I guess. Yes. So we have all this stuff, and we're going to put them together. So this is how it looks like with the tone mapping. Normally, the tone mapping is done last. It's pretty much the last step. But here I'm showing it with the tone mapping because it's a little bit easier to understand the image. So our engine is a forward renderer. It's not a deferred shader. So all those textures would be kind of they're not the equivalent of a G buffer. But anyway, so we have those buffers that I just showed to you. And one first thing we're going to do is do the motion blur. So here is how it would look. Yes, so here we have our color buffer with the motion blur. Plus, there is some very little color aberration that might be difficult to notice, but it's there. I like very small values, not crazy stuff where you're going to separate RG and B. Just a little thing that gives a taste with the image, but you're not quite sure what's happening. The next step is, okay, very difficult to see. I just added some lens flare. So just to make it, oops, that's not what I wanted to do. So just to try to make it more visible, I'm going to remove the original image and just show the lens flare alone. So yeah, that's the part we added. So that's done with the blurred light image that we add a couple of times, and we multiply it by red and do some crazy modifications to it. So that's how it looks. So it's difficult to see, like it's very subtle, but here you have a little bit of a patch of light, and here you have another patch of light. Then the next step is we're going to add the light streak that we had. Oh no, sorry, that's another. I'm still adding some lens flare, so I bet none of you saw exactly what happened because it's quite subtle. So I'm going again to remove the original image. Yeah, even there I don't even see what's happening. So let's forget about it. And then we add those light streaks that I showed. So I showed to you earlier the texture. So I'm just adding it on top of it and multiply by a small value, and we get this result. And so the image at this stage is looking like that. And finally, we have like a more subtle effect. We're going to add the vignetting. We're going to add a little bit of a grain. So yeah, here, like it's now you saw the difference. But if I just show you this image, it's kind of difficult to see where it is. But yeah, we have this vignetting that makes the corner a little bit darker. This is based on. If you read about vignetting, you're going to see a rule about cos 5. So I leave it up to you to read this stuff up. So it adds a taste to the image. I really like it. And that's pretty much about it. One last thing I wanted to show to you is, so we have this modification that is in progress. So I'm going to put back remove again the image. So it was looking like that. Oh dear, that's not what I wanted to do. Sorry about that. Let's do this again. Hop. So I remove the original image just so we can see clearly. Yes. So that's the current state, and that's how the demo was released. But I did some experiments, and you see the difference here. So this is like a different kind of lens flare. It's just an experiment. I thought it was looking cool. There are many things to try. You've seen yesterday the 64K competition. You see the current level of the post-processing. It's way above this. Like this is 2 years old. It was a little bit below the average. So you saw the Mercury demo yesterday. You saw the conspiracy demo yesterday. So there is really some crazy stuff going on. You can really explore a lot of things with the lens flare. So where is my demo? I'm going to remove it from the screen right now. Hello, up, come back over here. So yeah, that's what we get right now. Am I going to be able to get control? Yes. So here are a couple of real-life lens flare that you can get. You have like some really cool stuff. You have these kind of things here that is really nice. You have like these kind of stuff. There are some demos. Like yesterday, some of them had this kind of really cool effect. The Mercury one was trying to do something like that. That's really cool. There was this paper that was using ray tracing to evaluate what those lens flares are and save that as a mesh and use a mesh to display those. There is some really cool stuff to do. Oops, sorry. Here is another example. So I like this one a lot too. Like you have a lot of those huge lens flares. It's very strong light here. Those lines here are probably quite difficult to do in post-processing. There has to be a way, I don't know yet. Anyway, so that's up to you guys. If you have questions, I invite you to shoot them right away. Maybe we don't have that much time for questions because I was so slow. But please, go ahead. Oh my god, I was so slow I got everybody asleep. No question? Okay, well, I count on you guys to do some really cool post-processing effects and something looking better than that, please. And yeah, do demos.